We've completed our review of one-dimensional forces in work. If you need more information on the topic, please refer back to the algebra-based course where this is covered in more detail. We are now ready to move on to two dimensions. This is where the force is not in the same direction or opposite the direction of the displacement, and we will need to use trigonometry. The work done to a system is the force times the displacement in the parallel direction, or work equals force d parallel. That is certainly still true. However, when we have a force that is not parallel to the displacement, we just want the component of the force in that direction. And that we're going to use vector components. Instead of pulling an object with the force horizontally, right, in this direction here, what if we pulled it at an angle to the horizontal? How would we interpret work equals FD parallel for this case? Let's assume here the object, even though we're pulling it up in this direction, is just moving in the x direction, so its displacement is delta x. Vector analysis, as we showed earlier when we did kinematics, you have to break whatever force you're looking at into components that are parallel to the x and y axis. So over here, here's our applied force. We're going to break it into a perpendicular component along the y-axis and a parallel component along the x-axis. You can see how the applied force makes an angle theta with the horizontal. Furthermore, by just using our basic definition, work equals force times d parallel, we see that the perpendicular component here does not contribute anything to the work done, so it will not increase the energy of the system. Work is only done by the parallel component because that is in the distance in the direction of the displacement. Using trigonometry, we find that F parallel equals F applied times cosine theta. Our basic work equation here, work equals F parallel times the displacement, we substitute in for force parallel, which we found is the applied force times cosine theta times the displacement. We just move around the cosine theta here, so we have F app times delta x cosine theta. In words, the work done on an object by a force is the product of the magnitude of the force, that's right here, the F app, times the magnitude of the displacement, which is the delta x, times the cosine of the angle between them. And again, this shows why it's so important to use math and physics. This entire paragraph is replaced by this simple and elegant equation. Instead of pulling the object at an angle to the horizontal, what if it is pushed? What changes? It's really no more difficult a case. We still have to find the component of the force that is parallel to the object's displacement. We go back to our free body diagrams. Even if you're pushing an object, you still show the force as starting at the object and pointing in the direction that it's making the object move, or accelerate actually. So here's our force, but if we do a free body diagram, we start right here. Okay, here's the object, and you can see the force pushing down in this direction. So we have the applied force like this. We resolve it into components, F parallel and F perpendicular. Here's theta. A lot of times I'm just not going to worry about what quadrant theta is and worrying about whether it's sine or positive, the sine or the cosine is positive, but I like drawing a picture, and then you can clearly see that the perpendicular component will be in the negative direction and the parallel direction is still in the positive direction. So we have that the work is F applied delta x cosine theta. Here's theta, and the perpendicular force still doesn't contribute because it's not in the direction of the movement. Only the parallel component contributes to the work.